When a message connected to two print objects prints to the max window, it is printed twice. Apparently, this happened in an order because one print appears before the other. But which one was the first to print? A double click in the max window on the printed message gives the answer. The first was the rightmost. This behavior is better traced by providing arguments to the print objects. When the order of the objects change, the order of printing appears to change as well. What we witness here is how the scheduler that is working in the background creates an order of things that need to be finished. The message is sent to one print object, displayed in the max window, sent to another print object, which displays it in the max window as well. At this point, the scheduler has reached the end of the list of things to be done, and it goes to sleep until a new event happens. Since the scheduler handles things in order, it will create an order when a single event generates two new events. The order is based on a right-to-left arrangement in the patch. This can be made visible with the use of a debugger. Control-click on a patch cord gives the option to create a watch point with the function break. The moving green dots represent the activity of the scheduler that is interrupted by each watch point. And indeed, when the order of objects change, the scheduler adjusts accordingly. Since the placement of the objects determines order, some patches may create unexpected results. Consider the situation where two values are added and both number boxes are required to trigger the calculation. The number box at the right requires an additional trigger to achieve this. This all works fine until the objects are given a different location. This result seems odd. It is important to understand that the patch works perfectly fine. But since the programmer didn't specify an order, Max does. Such situations can be recognized from multiple patch cords fanning out from a single outlet. Based on this, we can define the following rule of thumb. Fanning is dangerous. The question is how fanning can be avoided. The good news is that Max provides an object for this, called trigger. The object enforces an order at the outlets, always from right to left. Therefore, even if the print objects are reversed, the order remains the same. The help file shows typical usage and also that trigger can be abbreviated to the letter T. The solution to avoiding fanning applied to the patch on the left is to use a trigger that produces a bang from the left after an integer from the right. Regardless of how these objects are positioned, the functionality we expect will not be broken. The trigger object, which also may contain constant values such as symbols, forces us to think in reversed order at the time of object creation. Let's look at a few practical applications. The difference between consecutive values, also referred to as the running difference, requires the triggering of the calculation before the value is stored as an argument. Separating the fraction and a whole number can be achieved in this way. The plus object can't feed back into itself, but with a trigger, an accumulator is created. Here, a counter is used to produce index values for each item of a list. The counter requires a reset before the list is broken into individual items with iter. Then the index and item are packed together in a list. The trigger can also be used as a hub to which multiple messages can be connected. The argument L, indicating a list, deals equally well with triggers and integers. Here, a pop-up attribute to print is enabled. The ZL group object groups together items until a bang is received. The types of messages that a trigger can deal with are bang, float, integer, symbol, and list. Distinguishing between types can also be used to send specific messages to certain outlets. The route object can take types as arguments and creates outlets accordingly. An additional outlet passes everything that does not match. A very specific object that does something similar is the type route object. This object even can handle signals. The route object can also be used to select specific messages based on the first element of the list. Type indications, as we have seen with trigger and route, are also used when building lists with the use of the pack object. Here, a list is constructed by combining three integer values. In a similar fashion, lists can be unpacked. A variation of the pack object without the letter C has all its inlets hot. Another method of constructing lists based on the join object allows combining various data objects, including lists. The unjoin object slices off as many single elements as defined by the argument and creates an additional outlet for what remains. The join object defines a trigger attribute that allows for another inlet than the typical leftmost to become hot. When working with lists, it is important to be aware of the ZL object, which combines a great variety of functionality in a single package. For instance, ZL sum sums together all elements of a list. The help file of ZL is somewhat unpractical. Therefore, I created an overview of all ZL functionality, which makes it easier to search, for instance, based on type. The patch can be downloaded at this location. In order to combine what we have seen so far in a practical example, imagine the following. Suppose we want to create a random generator of which values that have been selected will not appear in a while because they are added at the end of a queue and only from among the first few we select a new random value. For instance, from 10 possible values we would choose randomly an element from the first 3 that are sliced off. Selecting the element can be done with ZLmth, which uses a zero-based index. That index is provided by a random generator. Everything that was not selected comes from the right outlet. The left outlet produces the random choice, which is also the element that needs to be added at the end of the list. It is this element that will trigger the join object. The other chunks are what remains after the random choice and what remains after slicing. The chosen element indeed appears at the end of the list. This list becomes the new starting point and is handed to a ZLReg object. The initial state, where all numbers are in order, could be improved by scrambling that order. Instead of listing the values manually, an USI object can provide them instead. The right outlet provides index values and the middle triggers when USI is done. Now, some parameters can be added, for instance the size of the chunk from which to select an element and the size of the list of all elements. Concerning order of execution, PD is potentially even more dangerous than max. When a value is subtracted from itself, the result should be always 0. However, it is possible to create a patch which generates a different result. This shows that here not the right to left rule applies, but another one. The order in which patch courts are created defines the order of execution. This suggests that using the trigger object is of crucial importance. Since PD only knows floats, the integer indicator does not work. When the trigger object is expected to receive a variety of input types, the anything indicator using the letter A can be used. Combining values in a list is done in a similar fashion. In addition, PD has a list object that can perform a variety of functions.